Let's begin with the summary of the previous lecture. In the last lecture, we covered two of the most important quantum algorithm. And then the first one was the factoring algorithm, and the second one was the Grover search algorithm. And then with the factoring algorithm, the origin of the quantum speedup were two-factor. The first thing is that with the assurance algorithm or in the factoring algorithm, we have to calculate the power of some random number, and then we have to calculate the modular division. And then the problem was we have to calculate this one not only for a single x value, but we have to try this one for a lot of numbers. And then if you have to do it with the classical computer, all you can do is just to use the loop. But with the quantum computing, you can actually create the superposition of all those possible values, and then you can calculate this one just by processing only once. So that was the first reason for speed up. And then another reason for the speed up was the quantum Fourier transform. So instead of measuring all the value, what you do is before your final measurement, you apply the quantum Fourier transform, and then this quantum Fourier transform is very efficient compared to its classical counterpart. And then yeah, these proper combination of these techniques actually will allow us to calculate the perform the factoring. And another algorithm was the Grove search. And then here, what we did was we started with some random, not random, but it is equal proportion of all the possible indices. And then as we apply the Grover operation, this vector gradually get closer to the solution vector compared to the non-solution vector. And then even though forgot to mention that this was related to the interference, but yeah, let me point out that what happens is initial some vector might be initially started with the superposition of the alpha and beta, and then yeah, there will be some kind of coefficient in front of these two basis vectors. And then what we do in the Grove search is reduce the amplitude of this A, and then, oops, sorry. Yeah, we want to minimize this value, and then we want to maximize this value. And then this kind of minimization or reducing and then increasing this value actually corresponds to the constructive interference, and then this corresponds to destructive interference. So even though yeah, I just showed this kind of protocol in the vector space visualization, what really happens is all the interference. So by destructively interfering, yeah, we minimize the probability of this measuring this alpha, and then we increase the probability of measuring beta. And then yeah, if I just calculate the amount of step we have to request the oracle query, then the number of the necessary oracle query is much smaller, and then it is its scale is like a square root of the necessary oracle query for the classical case. Today, we are going to change our focus to a completely different topic, which is generally called as quantum cryptography. And then, yeah, there are many terminology referring to quantum cryptography. And then, yeah, one of the one of the frequently used description is quantum communication. But somehow, I'm a little bit careful about this terminology because if someone hear about the quantum terminology, quantum communication, the first thing people are trying to think is that whether it is possible to do a communication, a data exchange faster than the speed of light. And then I kept emphasizing that even with the quantum entanglement, you cannot do a communication faster than the speed of light. So the and then yeah, but still yeah, because the one of the issue with the one of the action of the quantum cryptography is that distributing the secret key, and then the and because distribution of the secret key somehow sounds like or as the same as the communication. So that's why people, many people think that it is related to communication, but it is not. And especially, I will also emphasize that there is a different concept between the um, um, regular communication and then the distribution of the key. And then once you understand, then it will become more obvious why I'm careful about distinguishing the quantum communication from the quantum cryptography. Nowadays, sometimes people started to talk about the quantum internet, which I also don't like too much. And then yeah, because again, yeah, whenever you have some keyword, then a quantum version of some keyword, then people prefer to um, think that it is enhanced version of the classical counterpart. But some frequently, the purpose of quantum internet is different from what you are expecting from the um, classical communication or classical internet. Yeah, so yeah, I just want to point out that you should be careful when you are using these terminologies. And then when we want to discuss about the quantum cryptography, the most relevant topic is something called as a public key system versus the symmetric key system. And then quantum cryptography is not the public key system. If I have to make a distinction, generally, what quantum cryptography does is it is providing the key or the secret key for the symmetric key system. And then, well, yeah, probably many, in most of case, whenever you are doing some secret communication, yeah, when you are doing some online shopping, then you have to transmit your information about your credit card and then or bank account, bank um, information. Then how can you protect your information? And typical method people are using is the public key system. And then I will describe what the public key system. I will explain about the public key system in more detail in later lecture. But today I will just briefly mention that one of the most famous public key system is called as RSA public key crypto system, and then RSA is the acronym of the three inventors name, and then the yeah, one of the interesting feature of the RSA algorithm is that the security of RSA is guaranteed by the difficulty of factoring a large number. And then the problem is now I showed you that Shor's algorithm is expected to factor very large number in much faster speed compared to the classical computer. And so now the quantum computer became the threat to the current existing public key system. And that's why people are I started to worry about the securities system. And then before the concept of the quantum computer was became well became popular, then yeah, and then still yeah, because the full scale quantum computer is not available yet. still, yeah, people believe that RSA is very secure. And then to prove that, yeah, this is also the company name of the company. And then this company actually announced the challenge for factoring. Uh, and then yeah, nowadays, and then in that in that challenge, what as you can see here, yeah, in the past, yeah, it is now about 30 years ago. And then in that case, it was even difficult to factor some um, decimal number composed of the decimal digit of 100. And then and then the people and then RSA kept generating very large number, and then people were trying to factor them. And then once they succeed in factoring, then they got some rewards or a prize. So there has been a lot of interest in factoring. And then nowadays, as the size of the key increases, and then RSA people expected that no one can solve that within the given time limit. And then yeah, actually maybe yeah, this might be considered that the um, um, well, yeah, in some sense, people started to factor larger and larger number. Yeah, so they somehow stopped rewarding the price, because yeah, there is some chance that another people will just break this, and then they didn't want to lose the money. Anyway, yeah, so this, but still, yeah, RSA is, at least up to now, is considered as one of the secure way to protect your information. And another advantage of the public key system compared to the symmetric key system is that it can be also used for authentication. So authentication is different from the transmission of a secret, because authentication is to prove that you are you, meaning that how can you check your identity? So symmetric key somehow does serve such kind of job, but yeah, there is some kind of limitation when you don't. Yeah, um, symmetric key somehow requires some, at least requires some people to meet at least once. Yeah, so that's somehow the benefit of the public key system. But anyway, yeah, I'm going to yeah, in today's lecture, I'm going to explain about the symmetric quantum key distribution system, which is one type of the symmetric key system. And then let me also give you some brief idea about what does a symmetric key system mean. Let's say that we have two party. Yeah, so yeah, there is A and B, and yeah, in communication, yeah, people prefer to call the sender as an Alice, because we don't want to call A and B, and the receiver may be as a Bob. Yeah, of course, the rule might be changed, but this is just a typical terminology for two people. And then let's say that Alice want to transmit some information to Bob, but without but yeah, Alice wants to transmit in a secret way. So what they can do is distribute some key composed of binary digit. Yeah, so like a 0, 1, 1, 0, and so forth. And then they just share these keys together, and then they believe that this key was not leaked to someone else. And then what we do is that Alice wants to send out the real information, and then this information will be also represented in terms of the digital number, binary number. So it will be either 0, 0, 1, 1, and blah, blah, blah. And then what they do, what Alice does is she will encrypt this key with this information with the secret key by going through the bitwise XOR. In that case, the secret key will be generated, and then the role of the XOR is that if we have the value of 0, then it won't flip the original value. So the original value is 0, and then 0 will be 0. But if we have key value of 1, then the second bit will be flipped. And then the third bit, the third bit in the key is also 1. So the third bit will be flipped. And then the first bit is the first bit in the key is 0. So the data won't be flipped, and then so yeah, it will be something like this one. And then if you don't have any information about the key, secret key, then even if you receive this kind of information, there is no way you can decrypt. And then to decrypt this information, what Bob does is use the same secret key, and then apply the um, apply the XOR operation between this received encrypted message and the key by itself. Then, because now Bob has the secret key by itself, so Bob knows that he should not flip the first and first bit, and then he should flip the second and third bit. So yeah, right after receiving this encoded key, it will be um, something like 0, and then it should be flipped, and then this should be flipped, and this the first bit should not be flipped. So yeah, by doing this XOR operation twice with the same secret key, then yeah, you can recover the original message. And then if there is any eavesdropper, then the eavesdropper cannot tell yeah what was the original message, even if the eavesdropper has the full encrypted message. Before we jump into the main topic of the quantum cryptography, let me just briefly introduce the concept of the post-quantum cryptography. Yeah, if you are not careful in interpreting this this name, then you might consider that post-quantum cryptography means that the next generation of the quantum cryptography, but that's not the case. Here, what post-quantum means that post-quantum computer. So yeah, as I mentioned before, RSA is one of the popular methods to encrypt most of the secure message in the at this moment. But we know that quantum computing is threatening the RSA method. So to make a secure communication, we need some alternative. And then post-quantum cryptography means that post quantum computer. So after the quantum computer is fully developed, we need a new system of the cryptography. And so yeah, that's why it is called as post-quantum cryptography. Yeah, so and then yeah, one in principle, the quantum cryptography by itself can be also considered as a post-quantum cryptography, because quantum computer also cannot break the system of the quantum cryptography. But this keyword, post-quantum cryptography, is used a little general circumstance. And then yeah, but before discussing this one, yeah, let me just ask you this question. Do you think until the working quantum computer will be fully developed, is it safe to use the current security system? Well, yeah, let's see some of the problem. Let's say that when do you think the fully developed quantum computer be available? And then practical quantum computer, which can actually break the RSA security, will require a lot of qubit. Yeah. So for example, current one of the typical RSA secure key, the length of the RSA key length is the order of 2048 or even more than 4,000. Yeah, so that means that to develop the quantum computer, which can break the current level of security, then we need to develop quantum computer with more than thousands of qubits. And yeah, it will take a while until we can actually develop such kind of quantum computer. So yeah, let's say that depending on who you ask, yeah, it will be order of 10 to 30 years. So here, let's say that yeah, I will just take the conservative number, and then I will say that it might take 30 years to fully develop the large scale quantum computer. So, and then yeah, you might think that well, yeah, so we have about order of 30 years until the quantum computer will become threatening. So why, yeah, and then yeah, if we just start to develop some kind of new cryptography system, then we might be safe enough. And then unfortunately, developing a new cryptography system takes a while. And moreover, even if a good crypto system is developed, it also takes it takes another several years until that system will be fully deployed in the real application. So yeah, the problem is cryptography system is kind of a protocol. So until all other systems will implement those protocol, yeah, that takes time. So let's say that it might take another 10 years. Even if we start to develop a new cryptography system, it might take 10 years. And then you might think that, well, yeah, um, until the quantum computer will be developed, it will take much longer than 10 years. So maybe we are safe enough. Do you really think so? Um, and the answer is not really, because one thing you have to consider is that typically secret generally has some kind of lifetime. For example, national security, national secret. Yeah, let's say some if you watch some of the movies, then yeah, the yeah, I don't know whether you watched the movie JFK. Then there was a lot of secret in the CIA, but then the CIA will keep their internal documents for 20 or 30 years or something like that. And then let's say that yeah, you need to keep your secret, you need to keep your secret safe for about 25 years. And then you might think that, well, it will still take longer to develop the quantum computer. So 25 years of lifetime of a secret if the lifetime of the secret is about 25 years, then maybe we are still safe enough. The problem is until we develop this new system, we will still also generate new secret, which also requires another 25 years and another 25 years. And by the time we fully develop the new cryptography system, then we might be already too late, because by the time if Y is about 10 years and the Z is about 25 years, and then about 30 years, then if the quantum computer becomes available, then we are too late, because now this secret will become publicly available after even before the end of the lifetime of this secret. So that's why it is also very important to develop post-quantum cryptography. And then one of the popular approach is using some mathematically challenging problem. And then one of the such kind of problem is called as a lattice-based problem. And then based on this complexity, people develop the cryptography system. And then in general case, people generally refer this type of the cryptography, which only uses the um, mathematical complexity as the post-quantum cryptography. But in the larger sense, I think the quantum cryptography by itself should be also considered as a post-quantum cryptography, because again, quantum computer cannot break the quantum cryptography system. As I mentioned previously, the purpose of the quantum cryptography, or the goal of the quantum cryptography, is not the communication. What we really want to do is distribution of the secret key. So and you remember that I showed you that if we have some kind of shared secret key, and then if we have such kind of key, then what we really do is distribute that such kind of key to Alice and Bob. And what they do is using this one, and then if there is some kind of message which Alice want to send to Bob, then before she will uh, transmit, she first use the XOR, apply the XOR gate to each of the bit, and then when the Bob receive this encoded message, then Bob will decode it using the same secret key, and then and this kind of protocol is called as a one-time pad. And then in this case, because this secret key is used only once for each of the bit encoding. So there is and then this is proof that it has absolute security. And then you can see that if you have some random sequence for the secret key, then there is no way you can reconstruct this original information just by looking at this encoded um, information. So and then and one of the reasons why it is called as one-time pad is that if you even if this secret key is very complex, if you keep using the same secret key over and over, then there is always some chance that some eavesdropper can figure out the pattern embedded in this secret key. Yeah, I don't know whether you watched the movie called as Imitation Game, which was which is the movie about Alan Turing. And then the way Alan Turing kind of figure out the secret from um, the German military, or German army, is that by because German military were using the same secret key. Well, it is not exactly the same secret key, but they were encoding the same kind of content, and then by using some kind of thing over and over, always makes the entire security system vulnerable. So it is best not to use the same secret key more than once. So that is called as a one-time pad key. And then um, here the most important part is the key. And then what we are trying to do is safe key distribution. And then if you think about typical digital communication, because digital information can be always copied, and then as long as someone has same copy of the encoded part, then later that people can decode this information from using some kind of other method. So the most ideal situation is that we cannot have there is no way someone else can copy distributed key. And then if I have to somehow summarize why does the quantum key distribution works while the other some other classical method does not work, is that because quantum mechanics has the no cloning property, and then also the superposition principle. So yeah, the combination of these property allow us secure key distribution. And another reason is that secret key has a little bit different property compared to the regular communication. So let's say that we want to transmit this kind of random number sequence to from Alice to Bob, and the difference of the secret key compared to the regular communication is that secret key by itself does not contain any information. Well, yeah, this kind of statement might be confusing, but let me show you why I can claim in this way. Let's assume that Alice and Bob during their transmission, Alice and Bob feel like the second bit might be might have some kind of error, and then yeah, both of them agree that a second second bit might be changed during the transmission. Then they can just agree that we don't need this second bit. Then they just will remove from the sequence of the secret key. And if this was the typical communication, then they Bob will send that Bob didn't receive the second bit, and then Alice will try to send that bit back to Bob, and then they will do some kind of handshaking protocol so that they will confirm that the second bit has been properly transmitted. For the secret key, if you just remove this second bit, and then if both both parties remove the same bit simultaneously, then the remaining bit sequence is as good as the original one, because all we need is some kind of random number, and then the most important part is that they should always match, and then there is no problem if you just both of them agree to remove some of them. And another case is that, let's say that Alice and Bob feel like this block of the bit might be eavesdropped. Yeah, so if you have some way to confirm that maybe there is some chance that these bits were wiretapped, then they can just drop it. And then again, in this case, they don't need retransmission of the bit, because the remaining bits, the remaining sequence is as random as original one. So yeah, a secret key distribution is different from the typical communication, because there is no confirmation of the receipt, and then if there is missing information, then in the typical communication they should retransmit until it will be actually received. But here, that such kind of process is not necessary, because all the remaining part can serve as a good secret key. So yeah, if considering considering this kind of property, and then that's why I said that key distribution is different from the typical communication. And then the essence of the quantum key distribution is that when we are sharing this secret key, we are going to use this quantum key distribution, or we typically call this one as a QKD, as an acronym. So I will keep saying QKD, and then just to be reminded that the QKD means the quantum key distribution. And then once the secret keys are shared between these two parties, the rest of this process, encoding with using the XOR gate, and then decoding with the XOR gate, or transmission of the information, all of these are just a digital domain. So there is no quantum mechanical thing. And then the only part we need the quantum mechanical property is only for the distribution. So make sure that you understand the difference between the key distribution and the actual communication. And then yeah, even with the QKD, the actual communication of the information or the delivery of the information is done by this the lower channel. And then these are all done in classical domain. So then how can we achieve the goal of this kind of key distribution safely using the quantum mechanics? So let's consider sending some information using the photon. So if let's say that you want to transmit a key value 0 or 1, and then for each of the photon, you might decide that whether you will send 0, 0 or 1, 1 or whatever value, then whenever you want to send a 0, you want to send 0, then you will send the horizontally polarized light, while when you want to transmit one value, one bit value of 1, then you will choose the vertically polarized. And then if the receiver uses the right polarizer, the right correct angle of the polarization, then you the receiver or the if this is Alice, then Bob will exactly measure the transmitted information like a 0 and 1. And another case is that instead of using the horizontal vertical polarization, we might also decide to use the diagonal anti-diagonal polarization to transmit the information. So in this case, if we decide to transmit use this diagonal basis to represent the 0 and then entire diagonal to represent 1, then as long as the angle of the axis of the polarization measurement is correct, then the receiver will properly or correctly measure the transmitted information. The problem is what happens, the sender send the DA basis information like a 0 along the diagonal basis, but the receiver or Bob uses the HV basis measurement. Then what happens? Some kind of random number, because yeah, you can either only, yeah, because this will be projected to one of these polarization, and the received information will be either 0 or 1. What happens in the opposite case? If you send horizontally polarized light and then you measure it in the TA basis, then you will also have the same random number style. So you might say that why we would do this, but yeah, the QKD actually works. Utilize this kind of property to the full its extent. The first quantum key distribution protocol is called as BB84, and then the name came from the two inventors, Bennett and Brassard, and then they developed this kind of protocol in 1984. So that's why that's how this name was obtained. And then in this protocol, what Alice does is Alice wants to send out the secret key. So let's say that Alice wants to 1101111 and so forth. And then when Alice sends this information to Bob, she uses a single photon. And then yeah, if we just decide to use only HV basis as an encoding, then whenever you are sending the 1 and then or 0, then only the H or V polarization will be used. However, Alice intentionally mixes the basis. So independent of these detailed information or bit sequence, Alice also decides the basis, whether she will use the HV basis or DA basis. It is randomly chosen. And then yeah, so for the first two bits, she decides to use the HV basis, and then for the next two bits, she uses the DA basis, and then for the fifth one, she used the HV, DA, 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 HV, 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 and so forth. So that's she randomly chooses not only the bit value, but she also chooses the basis. And then what should what should Bob do? Well, yeah, Bob wants to receive the exact correct value. So for the first bit, for first photon, Bob should use the HV basis, DA basis, DA basis, and HV basis, and so forth. But BB84 protocol does not work in that way. Actually, during the transmission of the photon, Alice never tells Bob which kind of basis will be for each of the bit. So Bob should actually has some missing information, and then even under such kind of situation, Bob should do something, and even though Bob does not know what kind of basis is used for the first photon or the second photon, Bob just decides to rotate his own measurement basis. So what happens is that when Bob receives the first photon, he just randomly chooses between these two bases. And then for the first photon, let's say that Bob somehow selected a TA basis, and then if the horizontal vertically polarized light representing one arrives here, then what does Bob actually detect? We actually don't know. It should be random number because the basis does not match. So, and then let's say that by accident, Bob just measured one, and then even though this value matches, it is just randomly chosen. So it is just by accident, and that it has no meaning. What happens? What does Bob do for the second bit? Randomly choose between HV and TA, and this time maybe Bob might be Bob's choice is matched to the Alice's basis choice, and in this case, what kind of value do I get? Do I get random number again? No, because now the basis matches, so Bob should definitely measure one, right? And then what about the third one? Yeah, randomly choose, and then this time, yeah, they do not match, and then the output will be random number, and then by accident it might become the same. And then for the first one, yeah, the basis didn't match, and then now it is again a random number, and then you might get a zero, and then now yeah, Bob randomly chose HV again, and then now somehow by accident the basis of the Alice and then basis of the Bob are matched. And then in this case, Bob should definitely measure one, right? And then the on next one, yeah, Bob also match the basis again. And then in this case, one should be measured. And we keep just doing like this one. And then Bob will measure some value depending on whether um, the bases are matched between Bob and Alice, then you will get the correct value. And then when the bases didn't match, then you will get some random number. And then once the transmission of the photon is finished, then Alice actually tells Bob what kind of basis she used for each of the photon. So for the first one, HV, the TA, HV, and so forth. At the same time, Bob also tells Alice what kind of basis he measured, like the TA basis for the first one, and then HV for the second one, HV, TA, and so forth. So they only announce their measurement basis after the measurement is done, and then yeah, even when Alice and Bob shares the basis information, they never share the measurement result or the sended information. So and the reason is when Alice and Bob compares the basis, they basically do not trust the digital communication. Digital communication is always insecure, and then it can be wiretapped or eavesdropped. So before the transmission, they never shared, but even after the transmission is done, if they start to share the actual bit sequence here and or a measured value, then they are exposing their secret key. So that's not that what they want. But if they only shares the what kind of basis she used and then what kind of basis Bob used, then there is no more information. And then, but uh, but between Bob, Alice and Bob, there is one thing they can be sure because they know that for the first qubit, for the first photon, they didn't use the correct matching um, basis. So even though Bob might have got some random number, and then this random number might be matched to the transmitted number, they don't care because yeah, it is possible that Bob might have received some wrong number. So they will just skip the first qubit. And then what about the second qubit? They know that they use the same basis for transmission and for the sending and then for the receiving. So they will keep this case. And then they just compare the basis choice. And only when those basis change choices are matched, then they just start to keep. And then based on this one, then yeah, we can so when the same bases are used, then they can be sure that um, the value Alice sent and then the value measured by Bob should match to each other. And then now they can be sure that this is a good secret key. And then you might still wonder why, why Bob, why this protocol is designed in this way. Well, yeah, let's assume that so between Bob, with Alice and Bob, they they will make the same kind of choice. But let's rewind the entire situation when there is eavesdropper. So what eavesdropper does is that and then even though they have different spelling, people prefer to call the eavesdropper as an eve for easy pronunciation. So what does eve does um, do? Um, Eve cannot have any more information than Bob because before the transmission of the photon is are done, Alice won't tell what kind of basis she used for each of the photon. So like above, all Eve can do is randomly choose between these two bases, and then let's say that for the first photon, let's assume that Eve just chose the TA basis like Bob did, and then in this case, she might have obtained one by as a random. However, once Eve received one, then it is then based on this information, what Eve can do is that she will probably choose this diagonal basis, diagonal vector, because that's what she measured with this basis. And then because Eve want to hide her existence, so she will just retransmit this photon with this polarization. And when Bob receives, Bob will probably measure one. And then for the second qubit, second photon, again, Eve made the wrong choice in terms of the basis, and then in this case, the received number will be the measured number by Eve will be random, and then here assume that she just measured the zero, and then in this case, because she doesn't know what kind of Eve cannot know what kind of basis Alice sent. So yeah, if we'll just decide to retransmit the corresponding polarization, which is like anti-diagonal, and then yeah, in this case, I said that the action of Bob and then the action of the Alice will be the same like a previous case. So now, yeah, in the previous case, I assume that Bob will choose this HV basis like here, and then this one will be this polarization will generate some random number on on the Bob side. So yeah, let's say that maybe because it is random, yeah, zero might be received, and if we keep doing like this one, and then yeah, the choice of Eve is completely independent of the choice of the Bob, and then once the measurement is done, then again, Alice and Bob will share their basis information. So these basis choice for Alice and then basis choice for the Bob is shared. And then maybe Eve might also get such kind of information. But and then now what now, if I compare the measured result like before, yeah, then yeah, so because currently Alice and Bob are not aware of the existence of the Eve, and then yeah, they will just assume that though these checked the same these cases when the same bases are used, then the trans the sending the information and the received information should match. And then in this case, from the Bob side, this is the secret key from Bob, and then these are 111 100 are the secret key from Alice. And now you can see that they do not match always. Yeah, so yeah, sometimes they are different, and sometimes they are matched. And then yeah, so yeah, in the previous case when there was no eavesdropper, even though Alice and Bob does not match their bases all the time, but at, at the end of the photon transmission, when once they compare their bases, then at least they can figure out which of the photons are correctly transmitted, and then they will just extract the secret key based on this matching. And this time, when the eavesdropper is here, and if they just if Alice and Bob follow the same protocol, now they obtain the wrong, not mismatched secret key. So if Alice and Bob compare these values, then they can actually detect whether there was eavesdropper or not. Because if there is no eavesdropper, then there will be no error. But if there is some error occurring, then they can be sure that there was some eavesdropper. But there is some problem, because if you compare all of these numbers, then that means that they should compare these. The way they can do the comparison is sending the digital information, and then we know that sending the digital communication is insecure. So during the comparison, there is a extremely high probability that such kind of information will be eavesdropped again. So what is the solution for this case? Well, if Alice and Bob decide to compare only the sample of this secret key, then and then they will decide which bit they will compare only after the secret keys are generated. So in that case, they might say that let's compare the first one and third one, fourth one, and whatever, um, but the same slot one. Then, because if cannot predict which slot Alice and Bob will eventually compare, so she cannot just avoid eavesdropping for that slot. And so eventually, when they compare some sample sequence in the secret key, then they can detect whether there was any eavesdropper or not. So why does this work? And the reason is that I emphasize that there is some special property of the secret key. So as I mentioned before, if Alice send the secret key to Bob, and then in this case she used the photon, and then if they use different bases, yeah, so they realize that they for the second bit they did not use the same basis. Then what can they do? Yeah, then it is obvious that Bob would have received some random number. Then they can just drop this value, this bit, and then they will just continue. And what happens if they feel like some part, like this part, this part, during this part, they so they randomly selected some of the generated secret key, and then they compared that sampled value, and then during the first part there was no error, but during this interval they might detect that there was some increased number of error, and then what they can decide is, well, because during this interval there was some amount of error, so we will simply suspect that there was some eavesdropping, and then yeah, they will just drop the entire interval like this one, and then the remaining parts still serves as a good secret key, because we know that during this one, yeah, there was no eavesdropping because there was no error occurring during this interval. So if as long as there is no eavesdropping, then they can just keep this value. So yeah, if you consider this kind of property of the secret key, then the BB84 is a well-defined, very properly designed protocol. However, if what we had to do was transmission of the information by itself, then we lose a lot of information. So that's why we don't use the photon for the communication, but communication of the information. But photons are good for a good candidate for the transmission or the transmission of the secret key, or maybe I will say that distribution of the secret key. So that's why it is called as the quantum key distribution. And then here, what we used is that when it is in the superposition, then there is no way we can decide which value it will be. And also another important property is when we are sending out the information, we are using the single photon. And why is that? Because if it is not a single photon, more the main reason we are using the single photon is that the quantum state encoded in the single photon in the photon in the polarization, then that polarization state is a superposition. And then we know that according to the no cloning theorem, if you did not create that quantum state by yourself, then or the person who created that quantum state does not tell you how she or he created that quantum state, then there is no way you can reproduce exactly the same quantum state. That's what the no cloning theorem says. And because of that, there is no way if you just use a single photon as a transmitting media, then there is no way you can make a copy of that one and then try to measure any better than what Bob can do. So let me summarize the BB84 QKD protocol. Well, the first thing the first thing the Alice or the sender does is she decides what kind of basis she will use. So she randomly choose one basis out of these two possibilities for each of the photon, and then she also decides what kind of random sequence she will send, either 0 or 1 for each of the time slot. And then based on the combination of these two information, we'll choose one of these four possibility. Then what about the receiver or Bob side? Bob also, before he receives the photon, for each of the photon, he also randomly choose one basis out of these two possibility. And then once they measure the once Bob measures the um, one photon, then Alice and Bob repeat all of these procedure on for some block of the time, and then once the transmission is done, then what they do is Bob and Alice announces what kind of basis they chose for each of the photon. But and then yeah, this announcement can be done through a public channel, but they never tell what kind of value Alice sent, or what kind of value Bob received for each of the photon. So that's the common procedure. But this is not end, because what they have to do is detect whether there has been any of the eavesdropping attack. So what they do is they based on the comparison of the bases, they first generate the first stage secret key, and then this kind of secret key is called as shifted key. And then when the two bases for the same time, when two bases are not matched, then they will just discard the bit information. And once it is done, yeah, so based on they obtain the shifted key, but they have to do whether check whether there has been any eavesdropping or not. So as I mentioned before, if you have very long shifted key, and then yeah, Alice might have some value, and then Bob might have some value, then they will randomly choose the for example second and then fourth, and then they compare each of the bit, and then if there is any mismatch, then they can conclude that around that time there has been some eavesdropping attack, and then they will just either discard the entire block, or there will be some kind of protocol, some kind of pre agreed procedure. And then that's what the ideal QKD describes. However, in the real system, we should have to consider some more problem. For example, yeah, I said that we are sending single photon for each of the bit. However, even if there is no eavesdropping attack, there will be always some finite amount of error, because assume that you are sending single photon through an air, and then yeah, when the single photon is flying through the air, then air has because it is not a space, but it is space that area is filled with some air. So there might be some kind of wind, and then whenever there is some change, some pressure change in the in the air, then the refractive index of the air might be changing over time, and then such kind of any kind of change during the transmission might actually create some change of the polarization. So even though yeah, original polarization might start as a V, by the time it arrives, the polarization might be slightly tilted. So in that case, if you just measure with the HV basis, then there is no guarantee that you will always measure the horizontally polarized light. So that happens even without the eavesdropper. And then the typical system generally have some finite amount of error. And then when you want to transmit the photon over a long distance, generally you don't send the photon through an air, because if you want to share the secret key between the uh, between Seoul and somewhere else in the local area, then you cannot directly send out the photon. So what people use is a fiber optic cable. So inside of a fiber, then the single photon will be transmitted, but during the transmission, there might be still some error caused by the instability of the fiber optics, and then there will be some amount of error, and the typical system generally have order of 3 to 5% of error. So if eavesdropper occasionally eavesdrop, then there is some chance that you might not detect the existence of the eavesdropper. But on the other hand, if the amount of error generated by the just the partial eavesdropping, then the amount of information leaked to the eavesdropper is relatively small. So you can still uh, use that generated secret key. But before you do that, yeah, because you know that there will be some amount of error, so you have to correct those error before you use this as a secret key for your encoding. And then the way we compare is the way we detect the error is that something like a checksum. And then, yeah, for example, if you have some sequence of 0, 1, 0, 0, 1, something like this one, then the one way to compare these sequence without sharing the entire sequence is that something like you just count the number of ones, and then in this case there are two of ones, yeah, here and here, and this one also has two of the ones, and then in this case you might just compare only number of two, and then in this case you did not expose the entire sequence, but you can still compare the integrity or whether there is any error between these two sequences. Of course, if there are too many of the there is a higher probability of occurring error, then even though this one is flipped to 0, the other one might be flipped to 1. So in that case, you will have some problem in comparison in comparing those two checksum. So yeah, there are many types of checksum, but a basic idea is you extract you if you have very long sequence, then you will split into some subblock, and then you will and once the one if you have a block, then yeah, you will calculate some kind of checksum for each of the block, and then depending on how much is your error probability, the length of the block will be different. And then once it is done, then you might think that that is good enough, but that's not the case, because let's say that we use some very small block like only 2-bit block, and then in this case to compare this Alice information and then Bob's information, they might also just do the counting of one. And then in this case, let's say that they were 0, 1, and 0, 1. So you might extract the information that this these two the number of the one in these two bits, there is one of the there is one of the bit is one, and then you think um, before I share this kind of checksum information, the security of the original information, and then after we share this information, and then you should always assume that whenever you are comparing using the digital communication, there will be some chance of eavesdropping, and then if this information is leaked to the eavesdropper, the security of this value cannot be the same as the before, because if we know the fact that the number of the one in this sequence is one, that means that let's say that the first number is x and then the second bit is y, then we basically share the information that the summation of x and y is one. So yeah, before we share the number of one, then the possibility of these two bits are, there are four possibility like 0001, 10, and 11. But because now we leak the information that summation of these two values will be one, so the randomness is only reduced down to these two possibility. And then if more and more information is leaked to the eavesdropper, there is a higher chance that eavesdropper will guess the correct secret key, and that's one you don't want. So yeah, even though we might start with very long sequence, as we start to compare, as we start to compare the checksum value, then we are losing some randomness. And then in that case, you have to recover the randomness. And then, for example, here you might say that if we didn't share um, the checksum, then you might say that the randomness of this sequence is a bit of two. But after you leak this information, the effective randomness is only one because there are only two possibilities. So yeah, so you have to actually reduce your key length. And then the typical way to reduce the key length so that you will have only the necessary number of the random bit is that, for example, if you have 4 bit, but you feel like already 1 bit information is somehow leaked, then what you can do is, let's say that uh, you will have only 3 bit. So in this case, for the calculation of first bit, you might just add these 3 values together. And then for the second bit, you might just add these 4 values. And then for the third bit, you might just get the information from these 2 values, for example. In this case, you will be left with a shorter length of the binary number compared to the original one, but the secure randomness embedded in this original sequence is kind of maintained. So that's the idea behind the privacy amplification. So yeah, there will be also other types of privacy amplification, but the purpose of the privacy amplification is during the comparison for the error correction, there was some leakage of the information, and also as I mentioned, during the even without eavesdropper, yeah, there is some finite amount of error, and then we don't know whether that error was caused by the physical system limitation or due to the existence of eavesdropper. And then in that case, you simply assume that all those errors were caused by the eavesdropper, and then um, because you will have only partially lost information, so by going through the privacy amplification, you can reduce the length of the random key or secret key, and then each bit of the secret key become as safe as before original one. So yeah, this is a summary of the BB84 protocol. And then next, in the next lecture, I'm going to explain another type of the QKD protocol based on the entangled state.